So we have seen that we'll maximize quality factor for a given inner area, or I can just call for a given inductance value. Whereas if we see that while trying to do a practical design of an inductor, this inductor needs to be within some kind of square enclosing box. So within this enclosed square type of enclosure, if you want to maximize the inductance value, not the quality factor, just the pure inductance value, it turns out that it will depend on how we can maximize the A inner in the given bounding box. And for such a scenario, a square shape will be giving the maximum inductance in a given square type of bounding box. So a square shape maximizes A inner or inductance in a given square bounding box. And this, whatever argument we are making for a square, the same thing will also be true for rectangular. If a rectangular space is available for the implementation of inductor, and we want to just maximize the value of inductance, it is such a scenario, it is better to go with the square of rectangular shape. There is another point which is important when we talk about a circular shape, is that this circular shape is not always possible to fabricate on chip because of all the lithography process which are involved. It may not be always possible to properly transfer this kind of pattern. Circular shape is not always compatible with fabrication process. So what we do is, instead of drawing a circular shape for inductor, we try to approximate with an octagon where we have these 135-degree angles. These angles are still possible to fabricate. So it is close to circular but not circular. Octagon shape is more practical in terms of fabrication. So far we have been discussing about how to maximize the quality factor of an inductor. And if you want to maximize the quality factor of inductor, we can see that we need to increase the ratio of A inner to the perimeter. If we want to increase inductance while also increasing the quality factor, we need to go for a bigger and bigger this kind of shapes. If the inductance is of the order of nanohenries, we'll find that the bounding box requirement will easily exceed 300 cross 300 micrometer square, and many times it can be even bigger. So it is not feasible to keep on increasing the loop size to increase the inductance. So what we can do is, we are already aware that whenever there are inductive segments which are kept close to each other, then there is a mutual coupling. And the way this loop is found is mutual coupling is effectively reducing the overall inductance. So is there a way we can place two inductors close to each other and connect them in such a way that the mutual inductance actually adds to the overall inductance value? So that will help us in increasing the overall inductance while not consuming the increased area. So let's see if we have an inductor like this with the terminals, let's say P1, P2, and I want another inductor to be placed close to it with as high coupling as possible so that we can utilize the mutual coupling. The best way to do is placing another loop in the same plane next to the first inductor. So it is possible to place this loop on a different metal layer also. Here we are showing a case where all the turns, so all the inductors with their metallization are placed on the same layer. And let us call this as these two terminals as S1, S2. So I have this inductor L1, I have this inductor L2, and electrically we can see they have this circuit where you have P1, P2 and S1, S2. Now to understand the dot convention, we can very easily verify. So if a current is entering P1, it is going to create this kind of magnetic field, and this magnetic field is going to induce voltage or current in L2 in such a way that the induced current should flow in this direction. Okay, so if current is entering P1, the induced current should come out of S1. So based on this, we can easily assign the dot convention here. So if entering P1, it should come out of S1. And in such a scenario, if you want to connect these terminals in such a way that we get an increase in the effective inductance, we should then try to P2 to S1. But if we do like this, then the inductance between P1 and S2 is going to be, this is L1, L2. Let's say it has coupling of K12 or a mutual inductance of M12. Then if we see this L effective is going to be L1 plus L2 because of this dot convention 2 and so the same kind of connection we can create here. As per our understanding, P2 should go to S1. So we need to make this connection. When this connection is made, then these two independent L1, L2, which are mutually coupled, now will act like a single inductance value L1 plus L2 plus 2M1. These are also called as planar inductors because effectively we are creating this multiple turns on the same plane. Many times this is required because you have only one of the metal layers which is thick. So as to increase the overall quality factor, you try to use the same layer for multiple turns. These planar inductors can have different variations. For example, you can have a planar inductor which is wound in a spiral manner, and once you create this kind of structure, this inner terminal has to be brought out, and this is done at a different metal layer. So there is no connection here. Planar spiral inductor. Another structure we can have is where you have this circular loops on the same plane, but in a very symmetrical manner. And as a result of this structure, at one place there will be crossing. So you ensure that this crossing happens such that one of the metal is at a different layer. This is called as planar symmetrical multi-turn inductor. This is your yes. Right. So there is no restriction on using only 2 turns. You can go for an n-turn inductor depending on the overall inductance value required. And you can optimize what should be the metal thickness, what should be the spacing between these turns, so on, so as to optimize the quality factor and the overall inductance. Now, when we are trying to realize these inductors, we need to keep in mind that there will be also some other undesired effect which will come into picture. So when current flows in a metal, then we expect that current is flowing uniformly in the entire cross section. But at high frequency, because now each of these currents are also time varying, so they create their own time varying magnetic field, and overall the net result is that in the center region of the cross section there will be reduction in the effective current, and most of the current will try to crowd near the surface. So at high frequency we will see currents only crowding near the surface. This is your current crowding. The surface. Now we can see that the effective cross-section area in which the current is flowing is also reduced. This is called a skin effect. and the end result is there is an increased resistance seen by the current at high frequency. This skin effect, we can get an estimate of what is the region around it in which this current gets concentrated. That is also called as skin depth. Which is going to be equal to 1 by root over I f sigma mu. F is the frequency, sigma is the conductivity of the metal, mu is the permeability of the metal. The skin effect is important for our discussion because at frequencies close to gigahertz and for a given conductivity of, let's say, copper, the skin depth will be of the order of few microns. And in such a scenario, if we are using very wide metal so as to reduce the overall resistance, it will turn out that all the current is going to be crowded near the surface, and the increase in this skin resistance is going to overall increase the loss and reduce the quality factor. So this can be modeled by adding an extra resistance in series with the inductor. So this is your L, this is R, let's say DC, and this is an extra resistance R skin added in series, and we will find that this resistance will increase with frequency, and you can assume that entire current is only concentrated near the surface in a thin layer of skin depth, let's call it delta. There is another issue takes place when we have multiple metals placed in close proximity, and this happens when we are using these multi-turn inductors. Generally, when the current is flowing, it is uniformly distributed along the entire surface. As the frequency increases, again, these currents are going to create their own magnetic field, and as a result of this magnetic field, it is going to induce some eddy currents in the neighboring conductor, and the end result is at high frequency. So if the currents are flowing in the same direction, so they tend to crowd again away from each other. So the effective cross section in which the current is flowing again reduces. This is called as proximity effect. And depending on the direction of the current, if they are, let's say, flowing opposite to each other, then they tend to crowd near the surface they are facing. So the net result is overall resistance again is going to increase at high frequency. And to model this, we can add one more resistance in series in the inductor model, and we can call it R proximity. So as the frequency increases, these two resistance will start increasing, and the net result is the quality factor of the inductor as frequency increase drops. So in addition to this effect due to the magnetic coupling of the currents, there is also capacitive coupling. So let's say I have a multi-turn inductor. And I take a cross section. And the cross sectional view will look like this. Here, these two metals. Again, metals here. In addition to these metals, there will be substrate. This is P minus lightly doped silicon. These are the metals. Okay. So there will be this capacitive coupling, electric coupling between these metals, as well as there will be coupling to the substrate. So this inductor, which we are expecting that to act like a perfect inductor, will have this capacitances present in addition to the overall inductance, and this capacitance at some frequency will resonate with the inductance, and beyond this frequency the inductor may start acting like a capacitor. And in addition to that, this substrate will also be lossy. The substrate can be modeled as a lossy dielectric. So the inductor model which we saw earlier, which had just a inductance and a resistance, now it needs to be modified to account for all these various capacitances which may be present. By adding a capacitor between the terminals, then adding this capacitor to the substrate, and the substrate itself will be modeled as a lossy dielectric. And these are the terminals of the inductor. So let's say these are the terminals P1, P2. So here we have got this P1, P2. This is the L. This is the R loss, which includes the DC resistance, skin resistance, proximity resistance. This is some CP. Let's call it CC. C sub. And if the inductor structure is not symmetrical, so these coupling capacitance, substrate resistance may also be not identical. So this model of the inductor captures various non-idealities, and this model is kind of accurate for this gigahertz frequencies in which we are interested. If we go for even higher frequency, we find that many times we may have to add more sections of these elements so as to incorporate the distributed effect. Model of on-chip inductor. If we look at the frequency response of an on-chip inductor, we'll see that we find the impedance between P1 P2 as Z, yeah, which can be written as J omega L effective plus some R effective. We can plot the quality factor of the inductor with frequency. Where this Q inductor is defined as omega L effective divided by R effective. We'll see that as the frequency increases, the quality factor of the inductor also increases linearly. But because of the skin effect, it starts reducing. The increase in the quality factor, which we expected linearly with the frequency, is slowing down. And then other losses also kicks in. So as a result of which, the Q starts dropping rapidly. And beyond frequency, we will see that the Q becomes negative. At this frequency where the Q becomes 0, L effective actually has become 0. And this is happening because there is a capacitance in the inductor model, as we have already seen, which makes the net reactance to be 0 at resonance. And beyond that, the reactance becomes capacitive. So this is the self-resonant frequency. So when we are trying to design an inductor, we want to operate somewhere here close to the maximum Q which we can achieve from the inductor, and we should also stay away from the SRF because around the SRF the value of inductor changes very rapidly. So here it is inductive, here it is capacitive. Now we have got some idea about this planar inductors. We can as well talk about coupled inductors, or many times these coupled inductors are used to design balance. So this balun requirement is that we may have a single-ended input needs to be converted into a differential output. So this is converting an unbalanced source to a balanced source. This is why it is called as a balun. And we can see that this balun can be easily realized with the help of this mutually coupled inductor. Similarly, many times we use this coupled inductor for impedance transformation. So these coupled inductors are really useful at high frequency. Now let us see how we can realize this coupled inductor. So we are already aware about the planar inductor. If we want to add another coil which is coupled to this coil, we can do it on this same plane like this, and then take an underpass. This is going to be and here we can also note down the dot convention. So let's say these are the terminals. So we can very easily see that once the current is entering this P1, it will induce the voltage or current in the L2 in such a way that current is going to flow in this direction. So it means if current is entering P1, it is going to come out of S2. And this idea can be extended to multi-turn coupled inductors. For example, we can have and L2. This is your L1. This is your L2. Here we can see a 2:1 kind of. See. So here you can see a 2:1 coupled inductor.